Okay, so we have these problems. Identifying the zeros, the numerator, zeros, the denominator, asymptotes, and then what's the implication of these things for the graph? Okay, so let's just say the first one is okay. So the first one is wouldn't be this for these A's, B's, and C's for anybody's name, but so good. Okay. Then numerator is 0. If x minus 7 equals 0, x squared plus x plus 12 equals 0. Okay. Well, x minus 7 equals 0. Or x equals -1 plus minus square root of 1 squared minus 4 times 1 times 12 over 2. Okay? Because this is a quadratic. Now it's easy to get used to saying, well, whatever number's here is going to give you 0. The opposite number is going to give you 0. That's true if you have just an x, okay, plus or minus a number. Not true if you had like 5x minus 7. You'd have to be a little careful about that. And of course, it's almost never going to be true here. This number will almost never give you 0. If you put in -12, you get 144 minus 12 plus 12, which is 132. It's not 0. Okay? It doesn't work at all. You got to set the thing equal to 0, meaning you have to then identify that it's a quadratic and use a quadratic formula. Okay? Okay, this can't be, this is not a real number, right? So x equals 7, you're only 0. So the denominator if x plus 10 is 0, or x minus 14 is 0. So it's true if x equals -10, or x equals 14. Okay. So I've gone into all the possible detail, which is tell you about the graph. Well, numerator is 0 if x equals 7, the numerator is 0, and the denominator isn't 0, and the denominator isn't 0 if x equals 7. Then x equals 7 is 0. And here's 7 on the x-axis. And the graph has to go through this point. If the denominator is 0, then as x gets close to that 0, like if x gets close to -10, then the denominator gets really small. Okay? A small number goes into whatever the numerator is a lot of times. And the smaller this gets, that is, the closer x gets to -10, smaller the denominator is going to get, the bigger the numerator is going to get, or the bigger the whole thing's going to get. So that you get a vertical asymptote. Okay, so when x equals 14, we draw a dotted line indicating we're going to have vertical asymptote there. And at x equals -10. Same thing. Vertical asymptote. Okay. Now there's more. If we plug in, if we want to get the graph, we want to plug in x equals 0 to find the y-intercept, right? Okay. Well, all the zeros just give you 0. That's going to give you -7 times 12 over 10 times -14. That's going to be 84 over 40, 140. And coincidentally, it equals 0.6. So we have the point here. .6. Now you go to the left, x is going to be a big negative number, right? If x is a big negative number, this, and this are all going to be big negative numbers, aren't they? If x is -1,000, then all these numbers are pretty close to -1,000, aren't they? -1,010 is -990. That's pretty close to 1,000. So it's almost like you've got -1,000 here, -1,000 here, -1,000 here. Okay. This is going to be close to 1,000,000. If you square -1,000, you get 1,000,000. If you add -1,000 to 1,000,000, you still get -900. You get 999,000. Okay, which is close to 1,000,000. And 12 doesn't contribute a drop of anything, not much to that. Okay. So the idea is simply that this is like -1,000 times 1,000,000. That's like a -1,000 times 1,000. This is a lot bigger than this. Now the rule is your leading term, if you would expand this, would be x cubed here. It would be x squared here. Okay. X cubed over x squared is like x. So for a big negative number, you're going to have 3 negatives and a positive. It's going to give you a negative. 3 negatives give you a negative. When you multiply or divide, doesn't matter. 3 negatives are going to give you negative. Okay, so it's going to be negative and it's going to be big. Okay. Now the other thing is you do get a slant asymptote here. And to calculate that slant asymptote, I'm not going to do it. Okay, because we're just trying to prepare you. If you understood it and if you saw it, even if you just saw it and tried to work with it, then when you see it in free calculus and we do it in detail, you'll understand it better. Okay. What we're trying to do is prepare you for free calculus. We don't want to take enough time to go through the long division. But what you do is you multiply this out, you multiply this out, and then you divide the numerator by the denominator using long division. That gives you a slant asymptote. I'm not going to deal with that except to say, okay, it's going to go to negative infinity. The degree of the numerator is 1 greater than the degree of the denominator. So it's going to go along a straight line. It's going to be negative. So it's going to come up like so from negatives. And it's going to approach this line as an asymptote. It looks something like this. And then on the other side of 10, thing is going to flip. Oh, we can't do that. Never mind, it's not going to flip. It's going to come down from up here and go through this point. It has to go through 0 here. Then it has to be asymptotic to this. Well, it's going to come down like this. It's going to kind of level off. Go through 0 here, and then it's going to go down like this. The big point you want to take away for this class is that you have vertical asymptotes. And you've got to go through the x-axis only at the zeros. And you've got to go through the y-axis at the intersection. Okay? Got a question? Okay. Good. Okay, question was, does the slant asymptote cut through? Well, yeah, the slant asymptote actually does cut through, but there are no graph points on the slant asymptote. The slant asymptote tells you what happens when x gets really big in this direction. So this is consistent with the slant asymptote. This thing's going to keep approaching this line here. On this side, it's going to approach a line up here. Okay. Now on this side, it's going to be positive. That means it's going to come down. The way this is drawn, it's not going to work. It's going to come down from up here and then turn around and go up toward the asymptote. Can't really draw it on this side. Didn't leave myself room. And didn't want to talk too much about the slant asymptotes, okay? But you do want to concern yourself with the sign, whether it's positive or negative on this side, positive or negative on this side, and whether it gets big or not on each side. Okay? So that's kind of the way you do the graph. Now, this one is just this one upside down, right? Let's look at that. So if you got y equals x minus 7, sorry, x minus 14 times x squared times x plus 10 over x minus 7 times x squared plus x plus 12. Okay, well, the same stuff tells you that the denominator is now 0 wherever the numerator of this one is 0. So the denominator is 0 just at x equals negative 7. Numerator is 0. At x equals 14 and x equals negative 10. Okay. Degree down here is bigger than the degree up here. If x is a big positive number or negative number, then you have a big times a big, right? Divided by a big times a bigger big. because of the x squared. Something you're well off understanding rather than just memorizing rules about degrees, because you can forget those rules if you know the reason for them. You can think about it. So you want to think about what happens if x gets really big. If x gets big, negative, well then these three will be negative, but this will be positive because you're squaring the x, okay? So you'd have three negatives. It's going to be negative. The large x is negative. Positive, your large x is positive. Okay. X equals 0, y equals, well, you can just kind of write it down, kind of, you know, you're going to end up with negative 14 times 10 in the numerator, and negative 7 times 12 in the denominator. That's because all your x's and x squareds are going to be 0. You're just going to end up with negative 14 and 10 here, negative 7 and 12 here. Okay. And this equals you know, 140 over 84, which is reduces to 5/3 of the reduces to 6. Wait a minute. Reduces to 10 over 6. Well, that does reduce to 5/3. That's approximately 1.7. Now we have all the information we need to sketch a graph, a rough graph. It won't be exact. But our zeros are when the numerator is 0. Numerator is 0 at 14. And x equals negative 10. The denominator is 0 at x equals negative 7. So this dotted line is x equals negative 7. The y-intercept is at 10 over 6, or 1.7. So this is the point 0, 1.7, approximately. For large negative x, y is negative, and it's close to 0, meaning that you've got horizontal asymptote here. Comes down like this, probably down a little bit before it turns back up. And it does this sort of thing. Then on the other side of x equals negative 7, it's going to be positive. It's going to come down through here. It's going to go through 0 here. And it can't do that. So what's wrong with this? I'm running into a problem here. And I don't see what it is. If I come down here and then go through this point and this point, I get up below, I end up below the axis, right? But as x gets really big, this has to become positive, and I don't have a place to get back through the axis. So I don't see what's wrong with this. Let me look at it for another minute, but I don't want to take too much time on it. Positive there. Come through here. Then it's got to come above the axis. I'm just going to leave that the way it is, unless somebody's got a suggestion. I'm apparently missing something. Okay, somebody made an excellent comment that, well, sometimes it come down here and just touch here and go up. But that occurs only if you have an even multiplicity. If that's zero. That zero here comes from x minus 14 being equal to 0. And x minus 14 is just to the first power. That's an odd multiplicity. That means that in the vicinity of this point, the graph has to be like a straight line. It can't be like a parabola. Now, if you had a square here, then it could be like a parabola, just touch and go back up. Okay? So really good observation. And I wish it helped because I'm stuck. Okay? Then I hate to be stuck, but I don't see what's wrong here. Something is, looking at this graph, I know that this graph is going to be reciprocal of this, and that the asymptote therefore has to be when y is 0, which occurs when x equals plus 7. Okay, and being careless by nature, I wrote down x equals negative 7, right? Denominator's not 0 and x equals negative 7. So I don't know why you let me do that. But you all need to get on the ball, okay? Okay, it should be at x equals plus 7, and now it's going to be okay. So I'm going to erase everything. I looked at everything but that. Let's redraw this. I'll draw it down here to the right board. Now you see, in making that mistake, I just pretended to make that mistake. I didn't really make that mistake, but I wanted to illustrate my point here, right? I can tell by your faces that you really believe it. Okay, well, most of you are kind of laughing at me. That's good. I deserve it. Okay. The asymptote here has to therefore be where the denominator is 0, which occurs only at x equals 7, not. Okay. That's where our vertical asymptote is. Our y-intercept is still at approximately 0, 1.7. We have zeros at x equals 14. We'll put that 7 closer to the origin. I'll just extend my axis long enough to accommodate 14 here. And at x equals negative 10, which might be about here. Okay, now, if we put it together, we don't have an asymptote here on this side. We come up through negative 10. So it comes along here, probably dips down a little bit before it comes up, but probably not much. And it goes through here, and I've kind of missed that point, but comes up here. Okay. And that all works. Then on this side, it comes up through here, turns around and becomes asymptotic to the x-axis again. So there we have it. So that's it. Okay, we want to move on now. We're going to talk about exponential and logarithmic functions. And this gets actually easier, even though these functions are more sophisticated in a lot of ways. They don't have all the detail that you got to worry about. There are plenty of details. But the algebra gets simpler if you remember a couple of simple rules, and you end up a lot happier than you are with rest. Yeah, okay. Hopefully you remember that the basic exponential function y equals 2 to the x. But if you need a reminder, you just got one. Okay. You make a table. And here's the table. In the graph. Looks like this. If I extend it, this curve looks like this. It goes up really fast. You know, if you go up to 3, it goes up to 8, so it goes up to a point twice as high as this one, so it goes up to here. And then it goes up to a point twice as high as that, and it can barely reach that high. And then it goes twice as high as that, which gets pretty close to the ceiling. So by the time you're out to 5, you're up near the ceiling, okay? And by the time it gets to 10, you're mile high, okay? Or close to it. Okay, so that's the basic property of the exponential function. Well, how would you complete this? What happens is x goes to negative infinity. I'm just going to say this, I'm not going to write it all out at this time. As x goes to negative infinity, what happens? Okay, well, if x goes to negative infinity, you can start by thinking what happens if you have -3, then -4, then -5, right? Well, if x is -3, 2 to the x is going to be 2 to the -3. You should know that's 1 over 2 to the third. And 2 to the third would be 2 times 2 times 2. That's 8. So it's 1/8. If x goes to -4, it's going to be 2 to the -4th, 1 over 2 to the 4th. 2 to the 4th is 16, 1 over 16. So your values go like 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. By the time you get out to -10, it's 1 over 1024. Okay. Now, all those numbers are positive, but they get really small really fast. Okay. By the time you get out to -10, which isn't all that far out here, you're down, well, so close to 0 that you're within the line of the x-axis, if you draw any line at all. Okay. 1/1000th of this. Okay. That means cut it in half again, keep cutting in half 10 times. It's really small. Okay. So y goes to 0. You keep going this way. Every time you move to the left 1 unit, you get twice as close to the x-axis. In other words, your value of y gets half as big. If you go this way, every time you move 1 unit to the right, y gets twice as big. So clearly y approaches infinity here. All right, well, that's worth knowing. Now, y equals e to the x is actually even more basic than y equals 2 to the x, but e is a little harder to deal with. Although your calculator deals with it fine. You got an e to the x button on your calculator. Okay. Well, e is approximately 2.718. Between 2 and 3. Yeah, roughly ballpark twice as close to 3 as it is to 2. Okay. Now, if we make a table for y equals 2 to the x, what if we get 1/4, 1/2, 1, 2, and 4? If we did 3 to the x, we would get 1/9, 1/3, 1, 3, and 9. Now, you understand what I'm doing here. I'm not making the table, labeling everything, but we're very familiar with these tables. So it's pretty easy to construct a graph of 2 to the x and a graph of 3 to the x. So let's do that. Now, we need 9. So I'm going to put 8 here. So that's easy to subdivide. So here's 1, here's 2, then 3, and so forth. And I can put 9 up here. Okay, so here's y equals 8. If x is -2, then 2 to the x would be, of course, 1/4. And then you got -1 and 1 and so forth, and 1/2, and 1, and 2, and 4. So there's your graph of y equals 2 to the x. It looks a little flatter because I had to use bigger numbers on the x-axis. Now, if I want to do y equals 3 to the x, 1/9 is actually less than 1/4. 1/3 is a little less than 1/2, and it still goes through 1, but then it goes through y equals 3 here and y equals 9 here. So the graph is actually lower than the 2 to the x graph until you get here, and then it goes up higher. So this is y equals 3 to the x. So if you want to visualize y equals e to the x, just visualize the 2 to the x and the 3 to the x graph, or sketch them quickly. This takes a minute to sketch them. And then e to the x is going to be in between these, probably a little closer to the 3 to the x graph. So e to the x, not coming out where I want it to, but Okay, it's not very well drawn to the left of the axis because the numbers get really close to the x-axis and the chalk just won't write where I want it to. But that's like y equals e to the x, okay? Yeah, it's not a very well drawn graph, but you got the picture. That it looks a whole lot like your basic exponential function, but it moves away from it faster and faster as you go to the right. And it's down below the 3 to the x graph if you want that graph as an example, okay? You'll recall, I was going to write it out, I was debating, I'm not going to write it out, looking at the time, that the log, base 2 log function is just the inverse of the 2 to the x function. So if you want the base 2 log, you just switch these columns and you get the log. That's how you do an inverse graph. If you got the graph of a function, you get the graph of the inverse by switching x and y. Okay, that's background. Let's say you have now the point. On the graph of exponential function. Y equals a times 2 to the x. What's the value of a? Well, this point tells you that y equals 8 when x equals 3, right? So y equals 8 when x equals 3. You know, I knew I didn't want to use 8 there. I better change that 8. I'll change that 8 to 10. So now this says that y is 10 when x equals 3. Okay? Well, we can find what a is. We can solve for a. N equals a times 2 to the third. 2 to the third is 8. So 10 over 8 is 8 times 8 over 8. A times 8 over 8 is the same as a. If you want a over 1 times 8 over 8. equals A. So A is 10 over 8, which is 1.25. Very simple. If we have a point and we know function, except for the number out in front, then we can solve for that. And of course, A is your vertical stretch factor. So you just take the 2 to the x function, vertically stretch it by a factor of 1.25, move every point 1.25 units further from the x-axis. And you have the graph of the exponential function that passes through this point. Okay, well, let me just ask you to do a quick exercise. Y equals A times 2 to the x. You have on that graph the point A, or A and B, or your A and G numbers, okay? So find A. A is the vertical stretch that you would use on the 2 to the x graph. Okay, so we can easily do this. And just a few steps. If A, y equals A times 2 to the x, and A is, let's say, 7 and G is 23, then the logic is y is 23 when x is 7. If y is 23 when x is 7, is A times 2 to the 7th. Okay, 2 to the 7th is 128, 2 times 2 times 7 times. There's some dots. I want you to fill in all the details of the calculation. You're going to do that A is 23 over 128. Okay. Now, if you start from the idea an exponential function is always something like this. So this number might be 2, it might be 3, it might be E, it might be 5.6 instead of 2. Okay. If you have a point on the graph, you can always plug in if you know what the form of the function is, okay? And solve for A. Now there's some more complicated questions that I'll let you worry about. If you do that much, it's not a bad start, okay? And I think everybody can do that much right now. So that's where you are. And we'll see how you do next time, okay? Some of the problems are a little trickier, but open math is going to give you plenty of support on it, okay?